All right, so this is the last question. This is about antiderivatives. Um, so you can see that I'm using what's called integral notation. So this is the integral sign. It has evolved from a giant script S, which Leibniz used for this purpose. This is the function that you actually want to find the antiderivative of. And this thing, you can just think of it as being a little flag that tells you what the variable is supposed to be. So, think of the formula for the volume of a cone. It involves two letters, H and R. So which one is the variable? So this little symbol is an indicator of that. And so let's just do it. All right. So for this first one, we want to find the antiderivative of x to the, what is 1 over x squared? It's minus 2, right? So the rule for doing these things is x to the n plus 1 over n plus 1. And so that works in the case where n is negative 2. The only time it doesn't work is, like, you can see that if n is equal to minus 1, then you're going to have 0 in the denominator, which is going to cause problems, right? So in that special case, the antiderivative is natural log. But this is not a problem. So what does this become? This is so this is going to be x to the minus 1, because negative 2 plus 1 is minus 1, and I put minus 1 also on the bottom, and so this is just minus 1 over x. Okay, and the first one is done. Now here we do the same trick. We just use the x to the n plus 1 over n plus 1 trick on each part of this polynomial. So it has 3 parts here. Oh, by the way, I should write plus c. So you're supposed to write. So if if this was plus 7 or something, then when I took the derivative, the 7 would vanish. And when you write the most general antiderivative, you include this plus c thing, because plus any constant will also be an antiderivative. And it's a consequence of the mean value theorem that those are the only antiderivatives. All right, so let's go piece by piece. So this becomes 2 times x to the 4th over 4 minus 7 times x squared over 2 plus 22x plus c. Okay. So that one is done. And what about this one? All right, what's the antiderivative of e to the x? Same as the forward derivative, because it's its own derivative. So this is e to the x, and now I use the x to the n plus 1 rule here with n equals 0. So you can think of 1 as x to the 0. So what does this rule do? It says that it should be x to the 1 over 1, which is just x. And this is just the backwards version of the fact that the derivative of x is 1. So it's e to the x plus c. Okay. And now we have hyperbolic sine. So remember that the derivative of hyperbolic sine is cosh. And the derivative of cosh is hyperbolic sine. Okay, so this 2 here makes things a little bit more complicated, huh? So what if you do this thing where you produce a rough guess? So as a rough guess, you might think that the answer is cosh 2x. But then when you test it, what happens? Take the derivative of cosh 2x, and by the chain rule you get hyperbolic sine 2x times 2. Okay. But you don't want the times 2. You just want it to be sine of 2x, or hyperbolic sine of 2x, because that's what you're trying to find the antiderivative of. But you can fix that by putting in a 1/2 factor. So 1/2 cosh, cos 2x will work, and do plus c. And for each of these you can check by differentiating what you get. So just check that if you take the derivative of this, you get hyperbolic sine to the 2x. And this one is just a memorization one. So this is, just like you have to learn the basic derivatives, you also have to learn the basic antiderivatives. So remember that this one is inverse sine of x, and then to make it general I say plus c. Okay, and that's all there is to it. I purposefully put a lot on there, and you should practice more. So you're not done studying antiderivatives just because you looked at the practice problem, because there are a variety of functions that you might have to anti-differentiate, and so you should practice more from the book. But that's it. Okay, bye.